Our next speaker is going to be Chris Bergland. Chris has been involved with the mapping industry for nearly 25 years and offers a diverse level of experience in cartography, geomatics, marketing, business development, and technical sales. Chris leads the sales team at Blue Marble and manages strategic relationships with enterprise customers through professional service projects and OEM partnerships. A native of Massachusetts, Chris holds a BFA, Bachelor of Fine Arts, from UMass Amherst. And with that, let's welcome Chris Bergland.
Thanks, everybody. All right, I guess I have a main job of keeping everybody awake after lunch. So, you guys are probably thinking, you know, Bachelor of Fine Arts. You know, why is he in the geospatial industry with a Bachelor of Fine Arts? Well, I majored in printmaking, so it was really the study of four-color science and how to print things. And, you know, that's where I came into the geospatial industry back in '93. I worked for an Atlas production company, and I've been characterized as a four-color man. Someone came up to me, shook my hand, "You're an ex-four-color man." I guess that's a club or something, I'm not quite sure. But basically, I mean, data accuracy is what I'm here to talk about. And back in the day when we were making maps on a light table, I mean, we would make the actual elements by hand. We would use, you know, scribe coat and actually scribe weighted roads by hand. We had this process called butt cuts, where we would get film positives from USGS, and we repaginated the atlases to a certain page schema that we would come up with. It would take 3 people to cut a film positive. You'd have a light table, like right here. You'd have a guy on one end, guy on another end, and then someone holding the ruler down. We're sitting there with loops. We called them loops. They were actually just linen testers, magnifiers. And we'd take the X-Acto knives on the actual tick mark of the film positive, and we would actually cut down halfway. The other person would cut the other half. And if you didn't get it right, that was a bad thing, because those film positives were expensive. But anyway, that's the level of data accuracy that I came into the industry with. And yeah, you know, I mean, throughout the years, I've seen a lot of different accuracy issues in terms of, you know, accuracy allowances of plus minus, you know, 10 meters. That was acceptable. Going down to plus or minus 1 meter accuracy, that was acceptable. So that's what I'm here to talk about, is just basically, you know, best practices for high accuracy geospatial data management. So you go on to best practices. So what are best practices? So I just stole the definition from Merriam-Webster, and basically it's a procedure that's been shown by research and experience to produce optimal results, and blah, 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 blah. So I work for Blue Marble Geographics. Assumably, most of you know who we are. Show of hands. Blue Marble Geographics? Okay, good. So basically, we've created our company through geospatial software that allows for data conversion, accurate data conversion. So what I'm gonna present here is essentially just an amalgamation of things that we've found throughout the years that people don't really realize that they do to their data, and then they call us up and then they say, well, this won't reproject right, or I've reprojected it and it's not lining up correctly. So, you know, I'm gonna go into basically high accuracy data, you know, what it is and why it's so important. I'm also going to talk about assumptions. Now, these little buggers, they're dangerous, and you really want to avoid assumptions. The age-old phrase, you know, what happens when somebody assumes, right? I probably don't have to finish that one. But we focused our assumptions down into 2 areas. Data manipulation, or basically touching the data in any way, and limitations. So basically, once you have your data processed the way it needs to be, now what do you do with it? Well, I don't know. What do you do with it? So we'll talk about that a little bit. And then once you've sort of recognized all of your assumptions, you know, maintenance of your data is really important. So you can break that out into education and training, and they're not the same thing. Education mainly is, I know the house I want to build and I can design the house, but training is I'm going to learn how to use the tools that's going to build my house. So high accuracy data. So essentially, data grades come in terms of accuracy. So consumer grade, you probably heard this, that's very loose, plus or minus, 3 meters allowance, basically atlases, where am I going? Navigational purposes really are what those are used for. Mapping grade, it's plus or minus a meter. Starting to get a little bit more accurate. For years that was an accepted allowance in a lot of industries. Basic location needs, what side of the street is the object that I'm looking for on. And then we've now come up to survey grade, which is plus or minus a centimeter or a millimeter. Oftentimes those are now involving things like time epochs and things of that nature. LiDAR is a perfect example of survey grade data that we're all familiar with now. 5 or 6 years ago, I wouldn't say that we were. A lot of people didn't even know what it was. So, when you're working with data that's both precise and accurate, that requires, care and persistence. Let me just get to my note real quick here. In terms of spatial data quality. So, the work isn't done when the data's been collected. That's sort of the beginning of it. Once you have your data, now you have to maintain it and make sure you don't screw it up. So spatial data quality is very important. And we've kind of broken that down into sort of 4 areas. You have your data completeness, or basically the totality of features that you're working with. Data precision, which can be termed as a degree of details that are displayed on a uniform space. And then we also have data accuracy. So that's basically the discrepancy of the actual attributes that you're mapping and what's supposed to be there. And then data consistency. So data consistency is basically termed as the absence of conflicts. So when we're working with high accuracy data, we would suggest figuring out what those assumptions are going to be, why they come about, why they're there, and how to avoid them. Data manipulations, understanding how you're going to change your data, and then the limitations of how you, now that you know what you've changed and how it's been changed successfully, how to keep doing that and how to overcome your limitations. So assumptions. So really when you get into metadata, think about it this way. So you work on a project and you work for this company for a long time and then you retire. And then someone who's doing a forensic analysis on that same area that you've worked on picks up your data 40 years from now, 30 years from now. What are they going to need to understand? Well, pretty much the same thing that you would need to understand if you had to go into that project right after you finished it and fix it. You have to be really clear on these attributes and the metadata that these attributes represent. So again, high accuracy data has much more metadata to keep track of, and it's not just going to be, an XML file that has, attributes you're concerned about. So if anything's absent, or it's not true, or it hasn't been checked or verified, assumptions are going to be made, and assumptions are basically guesses at that point. So this is a great slide. Now, you probably in the back, you can't see the small type, but essentially this slide was shared with me by Rebecca Baker. She's an archivist for NARA, or the National Archives Research Association. And this tells you basically all of the steps that come into play to archive metadata. And you can see it starts here with the, does this work?
Press the button and then
Put the button
turn
in
the
the
music
middle?
ring.
No. Okay, I'll stay here. So anyway, no, you have your data that comes from your producer, and you can see that it goes from, whoa, that's not what I wanted. Light. No, that's not what I wanted either. Oh, boy.
Oh my goodness.
What's going on? All right, I crashed PowerPoint, guys. Bear with me. Told you wouldn't sleep after lunch. All right. Where's the light? Was it the green button there? Okay, let's see what thanks. we're back. Okay. So essentially going from your data producer to your GIS clearinghouse, all of these steps are involved. Now, the flow chart on the right-hand side probably gives you a better idea in terms of what you're looking at. So essentially, you define your metadata. Basically, you characterize the data that you're looking for that needs to be connected with your maps. And then you have an inventory or evaluate the data. So basically, this is where you create a publication or a list of what this metadata should look like. And then you actually obtain and create. So we're down here now. We're going around this loop here. You identify the mechanisms for the collection or the purchase of the data. And then, that could involve anything from transformation, exchanging the data from two different organizations, and then you make the data available through access. And then the community will start to use the data, and then you'll also get to, develop strategies on how to maintain ongoing processes and procedures. So, you can see that it's a very, detailed process to make sure that metadata is correct, it's done the right way before it's even archived. So these are the things that can lead to assumptions if you're not taking this level of care to make sure your metadata is where it should be. So let's talk a little bit about plus or minus meter assumptions. So that's like sort of saying, well, I want to show my data, but I don't really care about the last 3 feet of it, it's close enough. And that assumption was excessive, it was acceptable for consumer grade data, but not really survey grade or even mapping grade. And the EPSG database, how many of you are familiar with that? Okay, well basically the EPSG database is a collection of all of the objects that we use to define the spatial relationship of the data, your projections, your ellipsoids, your datums, the transformations between the datums, the units that are supported, and all of these things. Most of the oil and gas companies that we work with are very familiar with the EPSG database, and they use that as their sort of, their repository to check a definition. You may have heard the term EPSG code as a reference to any of these geodetic objects. Well, basically, the EPSG database itself says, and I'm not going to read through all of these datums, but WGS84, everything that's WGS84, all the iterations. Oh, thanks.
Press it in, it goes to green.
Okay, sounds good. NAT83, a bunch of iterations for that, the International Terrestrial Reference Frame. All of those definitions, about 60 of them in total, are coincident at the plus or minus 1 meter accuracy assumption. So, that's because of that, and if you go back 20 years, a lot of the tools that people used for that amount of time, or since that time, have that assumption built in. And because of that, a lot of people have that assumption too. So, you look at WGS84 in certain places out west, in like California and parts of the Northwest, it's the same point that's in WGS84. In NAT83, it could be a meter apart. It's old ways of thinking that definitely need to be recognized. And if you don't recognize them, you're setting yourself up. I remember one time in 2005, we went down to Houston and we talked to one of the oil and gas super majors, and they admitted to us, well, we're just looking to drill a well, plus or minus 10 meters. That's okay for us. And we're just like, why are you using our software then? You don't really need it. But anyway, so more metadata assumptions. So we're looking at unit formatting. So unit formatting is often not included. Kind of reminds me when you got that toy for Christmas, assembly not required, or assembly required, meaning that you had to put the thing together after you opened it up. You have to find out what the unit formats are for your data a lot of times. Now we're talking things about like decimal precision, degrees, minutes, seconds versus PAC-DMS, decimal degrees, things like that. Data structure. How do you load in your data? Is it XYZ first? Is it YXZ? Is it ZXY? There were two guys that were part of the EPSG, and I think they still are involved. Roger Lott, who was the former lead surveyor for BP, and Roll Nikolai, who's the chief geodesist for Shell, they had a month-long debate about whether northing should come first or eastings should come first, to the point where I still don't even know what they decided. But I mean, that's really what, you know, people need to decide on a standard for their organization. Hopefully other organizations will catch on to that. Seismic data, you guys probably already know, you know, it's not, those headers are not uniform. You don't really know, you know, which column goes with which geodetic object, in this case, or datum, or what. Oftentimes when you do transformations or conversions on data, the metadata is not updated. And then datum transformations themselves. So everyone's clear on how a datum transformation works. You have parameters, and you're essentially performing an X, a Y, and a Z shift on a 3-parameter datum transformation. Sometimes you can use a 7-parameter that would include rotation and scale, things like that. Well, they each have their own. There's coordinate frame rotation, which basically goes from one direction, and then you have position vector rotation. That goes another direction. Some people don't even know, you know, that information when they're doing a datum transformation. The direction of the transformation itself, say, you know, you want to go from NAD83 to WGS84, it's not the same as going from WGS84 to NAD83. It's kind of like when you pull up Google Maps and you're trying to get directions to the new restaurant that your wife's been bugging you to take her to. You don't want directions from the restaurant to your house. That's after you've eaten, you know, but that's the same principle. So when is your data? Now, not where is your data, but when is your data? So now if WGS84 played Major League Baseball, it would be considered in the twilight of its career. It's 33 years old, 34 years old. The New York Yankees are the oldest, by average, team in the Major League Baseball, and that's 30.7 years. But, I mean, really, the Earth is dynamic, so the Earth hasn't stopped changing. WGS84 keeps getting updated, and I think Dave Doyle's going to talk tomorrow about that in greater detail. You know, they're not models fixed in time, so you don't really want to assume. And your coordinates, they're just not where they left them. I mean, look, here we have the San Andreas Fault. Let me try this out. There we go. You can see the San Andreas Fault here with all the points that are moving much quicker on the ocean side than on the land side. That's just what this whole time component, and making sure that these edits to coordinate systems that we already use, you know, they're applied. Right. So it's about time metadata. So HTTP, that's horizontal time-dependent positioning. That's basically factoring in your plate tectonic movement when you're doing a transformation. So that's been around for a number of years now. And new tools will, you know, new tools from the NGS, they'll factor in this epoch time. NAD83 and WGS84, they've been time capable for a while now. And this plus or minus 1 meter assumption of equivalence really hasn't been valid for a while, with the exception of that scary meeting I had in 2005 when it was really plus or minus 10 meters was okay. And then, you know, your epoch date. So that's really going to be a factor moving forward. It's basically the date in which the geospatial data was referenced. So NAD83 currently now has an epoch date of January 1st, 2010. But that's going to be a factor in the coming NatRef 2022, because that's going to be a time-sensitive reference frame. And we just all have to be aware about these assumptions. Now, data manipulations, onto this part. So any process from transformation to touching it, translation, going from one file format to another, transformation versus conversion. So when you transform data, you're actually implementing inaccuracy because you're taking a point on the Earth and you're applying a datum transformation to it, and you're actually degrading the accuracy of that data by doing a transformation. Conversion is mathematically derived, so it's replicable, and you can basically go back and forth 1,000,000 times doing a mathematical conversion, and you won't walk. The point won't creep, is what we've heard. Now gigs, this is a It's geospatial integrity for geoscience software. This was a movement that started in the oil and gas industry about 5 years ago. And basically what they did is they came to the geospatial vendors like us and they said, exactly what I'm telling you now, you know, there's too many assumptions in geospatial data. You have to implement processes for people to follow. Data auditing, that's a big part of it. Being able to replicate what you've done and essentially repeat it if needed. And you can see here the yellow star and all of these points are basically NAD27 points, but they're located on a NAD83 base map, and you can see the different transformations and how accurate those transformations were. NADCON being the one that you'd want to use, 15 centimeters only. But you can see the military regression equation, Canadian NTV2, these all introduce various forms of error up to the point of, you know, some that aren't geographically appropriate are off as much as 37 meters. So how to fix all this stuff? So basically going into solutions, you have gatekeepers, you have education, and you have training. Users themselves need to know how to make these right decisions. And education and training are key. They're not the same thing, and they're not just concepts, but how to directly apply them in your day-to-day. And even with training, high-level users need to guide them on working within the enterprise. You have people that have all this knowledge in an organization, and you get all these younger folks that come in, they need guidance. Enterprise-level business rules. Tell them what datums they can use, what transformations are applicable, what formats they can't use, and how to do these things. And then come to us, very much like what Gigs did, and say, you're a geospatial vendor, our company uses your software, you're responsible to make sure that these processes are in there. So we developed a suite of administration tools so that people can lock down the data source, they can make things available that they want to have available, and the other settings. So what have we talked about? Sub-meter accuracy, easier to collect, harder to maintain. Knowing these details to maintain are as important as maintaining them. And data doesn't get more accurate with manipulation, only less. So solutions here, we're talking education. GIS is a science, guys. I mean, there's a lot to learn. There's a lot of different consulting agencies and educational resources that you can employ within your organization. Policies. Once that knowledge has been established, don't backpedal on it. Go with it. Tell your other colleagues about it. Maybe you'll be the trendsetter. And then metadata, vague descriptions, they just lead to assumptions. And you know, you really got to bottle that down, or whatever. You really got to ratchet that down, I guess is what I'm trying to say. So essentially tools to support these policies. That, from us as a geospatial software vendor, that's what we've realized, and that's what we're trying to do for you guys. Tools need to support the user. You guys don't need to support broken software. If it's not right, tell the vendor about it and they'll fix it. And if they're not, you need to go to another vendor. You know, in software tools, ideally we try to make the best software we can for our users, but you do have to learn how to use it. And training is a necessary evil in terms of that. But hopefully you took something from this, and I appreciate it. Thanks very much.
We have time for a couple of questions.
I was that good? Because of no questions?
I got a question about when you're talking in the beginning about splicing maps together.
The butt cuts.
Yeah, and this is before my time, obviously, but did you ever come into situations where things didn't match up? And if so, who's the authoritative person to say which side of the two that you're matching was correct?
We would usually go with about 3 or 4 sources. We went with the USGS because the data was freely available to manipulate, but we would do a lot of research, and we would get state level maps, county maps, and you know, we would just sort of kind of make up our own authoritative decision at that point. You're talking back in the early mid-90s.
Yeah, because at some point you just have to go with.
You have to go with it,
one.
you know, and hopefully all of the sources that you're checking, you know, have the relatively same information you're looking for to solve that question. But yeah, we never, ever, ever relied on just one source. So, other questions?
Can you tell you a little more about the gigs and what in terms of people's perception about data accuracy in the oil and gas industry?
Well, yeah, so, you know, gigs really, they wanted consistency. So gigs is that geospatial integrity for geoscience software. So we weren't the only vendor that they approached, but we were the ones that had the more uniformly adopted transformation methods. So they sort of, you know, had us listen to their concerns and asked if we wanted to help them out. So essentially it was really implementing ways to go backwards in time, to see what processes had been done to your data, so that if they had to go back to a point and then take a left instead of taking a right, they could do that. So,
All right.
great, thanks very much, guys.